So talking about electricity, first we understand there are charge, right? There are positive charge and negative charge. And the charge, we have to give it a unit because one electron is too small. So we say, well, there's a big bunch of electrons together. And these electrons, I have a concept called charge. It's Q, or I can use small q, and then the unit for charge will be coulomb, right? And coulomb, okay. And then we define what is the current. Does anyone remember the definition of current? Yeah.
The rate of flow.
Okay, very good. Current is how much charge can go through a point in 1 second, right? So the unit will be coulomb divided by second, which is coulomb per second, which we give it a new name, we call it amp, right? So 5 amp means in 1 second will be 5 coulomb. That's gonna go through, right? So that's what it means, okay? So for example, e.g. 5 amp is the same as 5 coulomb going through a place in 1 second. Okay, and then we got the definition of voltage. Does anyone remember the definition of voltage? Yeah.
Just with that, would we get marked down if we didn't say amps is the unit? But instead we would just
Say coulomb per second. You wouldn't be marked down. At level 3, we don't care too much about units unless you particularly, yeah. But I don't think you're gonna get it wrong. I mean, current we always use amp, right? Yeah. Okay. So with voltage, does anyone remember the definition of voltage?
how much energy one can.
Yeah. So how much energy 1 coulomb charge gain or lose? Okay. If it's a battery, you're gaining energy. If it's a light bulb, you're converting electrical energy to light energy and heat energy, right? Okay, so then let's look at the unit. The unit is going to be joule. This unit is coulomb, so it's the same as joule per coulomb, right? And joule per coulomb, and then I give it a new name. I call it volts, right? So if you say a battery is going to be, say, 1.5 volt, what does this actually mean? It means for every coulomb of electron, how much energy are they going to gain? 1.5 joule, the joule per coulomb. Does it make sense? So that is what voltage means, and it's also called potential difference, right? Okay, and then we have two circuits. We have a series circuit, and we have a parallel circuit. Okay, when we have the two circuits, say if current equals to 2 amp, that means in 1 second, there's going to be 2 coulomb of charge coming through. Right? And then say if the voltage equals to say 12 volt, that means each one of these is going to carry 12 joule of energy. Does that make sense? Okay. And this tells you, well, current, what happens to current? Current stays the same. Because current is you counting the amount of electrons, the chuck. If there are 2 coming out, there will be 2 go through here, 2 go through here, 2 go through here. And the definition tells you how it's going to behave, right? So that's why current is going to be 2 amp, current here is going to be 2 amp, right? But if we look at voltage, voltage measures the energy the charge is going to use. If we say in this light bulb, this 12 joule coming over here, when it arrived over here, it only got 6 volt left. So how much has been spent over here? Oh, sorry, this should be 6 joule left. And then this will be 6 volt, right? And then the 6 joule is going to be spent in this one, then this will be 6 volt. That is the reason why in a series circuit, the voltage is going to be shared, because voltage measures the amount of energy each charge can carry. Does it make sense? Okay, and then coming to this one, say, well, I still say current is 2 amp, still 2 chuck. I still say this V is 12 volt, so 12 joule over here. And then this truck, one truck can go this way, one truck can go this way, because there are 2 ways for it to go through now, right? So that's why, and this is going to be 1 amp, then this will become 1 amp. Because it's splitting, right? Okay, And then the next thing is, well, how much energy is going to be here? So this truck has not spent any energy, so it will still have 12 joule, and they're going to spend the whole 12 joule of energy inside over here, becomes 0 joule. So how much energy is going to be spent there? That'll be 12, right? So that's why this is 12 volt and this is 12 volt. So that's why in a parallel circuit, voltage stays the same, but current splits. Does this make sense? Okay. And the next thing is this. Well, if I add one over here, what's going to happen to the current? If I add a bulb over here. If I add a bulb, now we got the equation voltage equals, I remember the expression this way. Current equals to voltage divided by resistance. Because current gives energy, it's a potential difference. We want a lot of electrons to travel through. But resistance is slowing the electrons down, converting energy. So that's why current is going to be equal to voltage divided by resistance, right? Okay, so if we add one over here, what happens to the resistance? Got bigger. If resistance got bigger but the voltage can't change, what happens to the current? Becomes smaller, yeah, right? Okay, if we look at this situation, if I add another bulb over here, what happens to the total voltage? Voltage can't change, yeah. So I equals volt over R. But now there are 3 ways for electricity to go through. Is it easier to go through or harder to go through? Easier. So then the resistance becomes smaller. Resistance becomes smaller, this one don't change, then it will increase the current.
In the
Yeah.
series, in the series one, doesn't the current stay the same?
The current,
For the third one, wouldn't it not be 2 amp?
it will not be 2 amp. It will be 1.6,
Oh,
for example. Yeah. But it will be 1.6 here, 1.6 here, 1.6 here, 1.6 here.
oh, okay.
So when we say current stay the same in a series circuit, it means when the circuit is set up, inside the circuit, everywhere is the same. But if you change the circuit, then the current is going to change. Does that make sense? Yeah. That's a common misunderstanding some people have. Okay, so, and you see, in NCA equation, they give you this equation, V equals IR, right? I don't like this equation at all. Because it says V equals IR, it's like V is dependent on the current and resistance. And that is not true. In reality, is the current can change, and these two are the independent variables you have to set at the beginning. Once you set these two, then that decides how many electrons can come out. Does it make sense? That's why this is a better equation. But they give this equation because this equation is easy to rearrange in terms of like doing math. So they try to help students not very good with math by giving this equation. But this is the ultimate equation that Ohm's law. What is Ohm's law? Ohm's law say the current in a circuit is proportional to the voltage we have, and then independently, inversely proportional to resistance. Okay. And then what is resistance? Resistance is this. Say if you have a wire, and these wire will have these nucleus, they'll have electrons, they'll have all these particles inside. And then when you have a negative electron coming, it's going to hit this one, it's going to move this way, 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 move this way, move this way. So however easy it is to flow through. And if it's very easy to flow through, small resistance. If it's harder to flow through, lots of resistance. Does it make sense? It also depends how many electrons can flow. If a conductor have lots of electrons, very easy to flow through. Otherwise, it could be very hard to flow through, right? Okay, and then the next part is this. Okay, so I'll write this equation over here. I equals to V over R. So the next equation is this resistance R total is going to equal to R1 plus R2 plus R3 plus blah blah blah. When series circuit, and that's easy to understand because you're going to be resist again, so the electrons pass through each one of them, so the resistance add together, right? Okay, but for a parallel circuit, we got this resistance equation, 1 over R equal 1 over R1 plus 1 over R2 plus this, right? That's how we calculate resistance. You were even taught this at year 11 level. So, but why does this happen? Okay, so why does this happen? We have this. So first, we define the voltage, the total voltage will equal to voltage 1, equal to voltage 2, equal to voltage 3, because that is a parallel circuit. Right? The voltage stays the same. And the current is going to split. Current I is going to equal to I1 plus I2 plus I3. The current is splitting, but the total current could increase. Okay, what do I mean? I mean this. Say this. Before I had this one, if that is 1 amp, that is 1 amp. Together is 3 amp. If I add another one, how much is this one? Still 1 amp. That is because these are individually connected to the voltage. The voltage did not change, the resistance did not change. This one will still be 12 volt, and it's still the same light bulb. So if you add another one over here, actually it doesn't change these two at all. Does that make sense? You can add another one, you can add another one, just like the light bulb we have. If one breaks, the other one will not become more brighter. Does it make sense? So people will be saying, oh, if there's another one, the current splitting to 3, so it must be less. But nobody say the current has to be the same. In fact, when you add another one, we're going to have more current coming out. Does it make sense? That's a bit of a difference from our common sense. Common sense is these are the food you have. If there are 2 people eating it, you will get more food, right? And then if there's another person coming, now you're going to get less food. And then another person, there's less food. That's how we commonly think about this kind of situation. If you add another one sharing, it must be less, right? But no, if you add another one, actually more electrons is going to come out. Does this make sense? Okay, if you put one here, 1 amp, 1 amp, you add another one, this one will stay at 1 amp, this one will become 1 amp, and actually together become 2 amp over here. If you add another one, 1 amp, don't change, this one will be 1 amp as well. And this one is actually going to have 3 amp coming out. Does this make sense? So adding one in parallel will increase the current coming through the battery. Okay, I'll write here. Say adding light bulbs parallel increase current coming from the battery. Okay, all right, so, okay, that's that part. Okay, so now we say, okay, I equal I1 plus I2 plus I3, right? Okay, and then what does I equal to? I equal to V divided by R total, right? Okay, what does I1 equal to? V divided by R1, because the V don't change, right? Or I can say V1 divided by R1. I2 equal to V2 divided by R2, right? That's my equation. Okay, so now I'm going to add all of this into here. V equals to R total equal to V1 over R1 plus V2 over R2 plus V3 divided by I3 plus bam, bam, bam. So I'm putting this one into there, right? And now you can see all the voltage are the same. So I cancel the voltage. I divide both sides by the voltage. So now I get 1 over R total is going to equal to 1 over R1 plus 1 over R2 plus 1 over R3. Right? Okay, so that's where this equation is coming from. Okay, all right. And then the next one is we have one more equation. And the one more equation is power. Power, by definition, is how much energy is changed per unit time, right? So the unit of power is joule divided by second, joule per second. But joule per second, we give a new name, we call it watt, right? It's to honor Watt, who invented the engine, the steam engine. So which started the Industrial Revolution with trains and it's all steam engine. So which is you heat the thing, boil the water, then the steam started pushing, and then pushing makes the thing start moving, right? Actually, one of my friends, he was doing a PhD at Auckland Uni Engineering. What he did was he made a little engine, and then he just put hot water in it. Once he put hot water in it, and then the engine started boom, 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 started like vibrating. Yeah, it was pretty cool. Very nerdy, but like really cool. Okay, so and then then we know the equation also gives you power equal to voltage times I. That's the next equation they give you, right? So why does power equal to voltage over I? Let's have a look. The definition of voltage we use over here is the change of energy divided by charge, right? And the definition of current is how much charge per second divided by time. When we time these two things together, you can see the charge divide each other. That equals to delta E divided by T, right? And then change of energy divided by time give you the definition of power, right? So that's where the power equation comes from. Why does power equal to voltage times I? Okay, and then the next thing is this. Well, voltage is going to equal IR, right? So I can actually combine these two equations together. Power is going to equal to I squared R. I write it over here because I can't see it. So V equals IR. So combine these two together, I can get power equals to I squared R. Because I'm replacing this into the V over here. Now it is 2I squared R. Okay, and I can do the same thing. Well, if I replace this I can go I equal to voltage divided by resistance. That's coming from my, here, right? So from the Ohm's law, and then I can combine, I can make it become P equal V squared over R. So power actually got 3 equations, but this is a common equation. And then these two are the derived equation. Does it make sense? Okay, so we can see like there's so much equations over here, but really it only comes down to 1, 2, 3 equation. And we know the mechanics equation, which is power equal change of energy divided by time. Even though your exam does not require you to remember any of this equation, but I always strongly recommend students to remember it, because by remembering it, you actually understand what it is. If you understand what it is, you can remember it. And then when you analyze a question, you know immediately, bam, this is going to be the concept I'm going to answer this question, because you got all these tools in your brain. Okay, yeah. So this lesson, I'm going to give you guys a little bit of time, just do some revision. I've given you the notes. So on your book, there is some questions on page 3. It says flow of change and transfer energy and then effective resistance. So I'm just going to give you guys some time to do that questions today. And then tomorrow we will move officially on to internal resistance, which is a year 13 stuff. And then we're going to be using all these concepts. Okay. And if you still need some help with the internals, you can get some help today as well. And just remind you, today there is lunchtime help session, so you can go to lunchtime help session as well. And Mrs. Khan will be helping students as well. Okay? All right, cool.